Hey peeps, we're going to go over Unit 7 Day 1 quizzes questions just to give you a chance to get a better understanding of how some of these questions are supposed to work. So question number 1 is asking you to identify acid-base conjugate pairs. Easiest way to do that is just to pick one of the things and identify the thing on the product side that differs by one hydrogen ion. In this case, it's going to be the propanoate ion. And then do the same thing with the other item, in this case, water. It's going to differ by one hydrogen ion to make hydronium. And then it comes down to your understanding of the definitions of acids and bases to identify what's the acid and what's the base. So as I compare the two things highlighted in pink, in order for this propanoic acid molecule to become the propanoate ion, it has to have lost a hydrogen ion or donated a hydrogen ion. So by definition, that makes this an acid, and this is going to be its conjugate base. The other pairing works a little bit differently. The water molecule, in order to become hydronium, must gain a hydrogen ion. And so if it's gaining a hydrogen ion, that makes this a base, and this is a conjugate acid. Once you've identified the acid-base pairs, it's just a matter of picking the option that most accurately represents what you've outlined there. Question 2. Which of the following substances is amphoteric? This is sometimes named anthoprotic. It simply means that the substance can act as both a bronzolaurie acid or a bronzolaurie base. Probably easiest is to work with the acids first. If it's going to be an acid, it has to have a hydrogen ion to donate, right? And so as you look at the answer choices, the answer choice D is going to be out right away. It cannot donate a hydrogen ion. The remaining options, right, could all donate a hydrogen. H3O plus could become H2O. H2SO4 could become HSO4 minus. And then HSO4 minus could become SO4 2 minus, right? These are just the subsequent things that would turn into if they got rid of or donated a hydrogen ion. So these could all potentially act as acids. The question then becomes, will they also, or can they also act as a base? So if hydronium is going to act as a base, that means it's going to accept a hydrogen ion and become H4O2 plus. Again, this comes with a little bit of practice, but you've probably never seen this before because it doesn't exist. So that cannot happen. H2SO4 would become H3SO4 plus. Again, maybe, right? I don't know. Some crazy chemicals out there. And then HSO4 minus will become H2SO4. The correct answer here is going to be C. If you're unsure, again, why B is ruled out, it just comes with practice, but recognize maybe as you walk through this sequence, the polyatomic ions that are negatively charged will gain hydrogen ions up until they become neutral. So for example, SO4 2 minus can gain a hydrogen ion and become HSO4 minus, and then gain another and become H2SO4. And now it's neutrally charged. At this point, we're not really going to see it gain any more hydrogen ions. I think the only exception to sort of where neutral things will gain hydrogen ions that you will see is H2O will gain a hydrogen ion to become H3O plus, and ammonia will gain a hydrogen ion to become NH4 plus, or the ammonium ion. That's just a standard kind of rule. Obviously, there's lots of bases out there, but this is just for the things that you most commonly will encounter. All right, finally here, question 3. It says, write a balanced equilibrium equation to describe an aqueous solution of bromic acid. You can do this two ways. I like to write it out like this, where I'm actually placing the acid in water, and then I show the acid donating the hydrogen ion to water to form hydronium. And then in this case, the conjugate base, the bromate ion, is left behind. But recognize that you can also write this without the water molecule. You're just showing that dissociation of the hydrogen ion, that donation of the hydrogen ion. Both of these are equally acceptable. You can write them either way. As you look at your answer choices, recognize that the one I've written here in purple is going to be the one that we use based on these particular answer choices. But if this were a free response, you easily could replace the hydrogen ion with hydronium. Both are completely acceptable. So like any K, it's concentration of products over concentration of reactants, you aren't going to include pure liquids. So water is out, even if you use that magenta representation. And it's to their stoichiometric coefficients, all of which have a coefficient of 1. All right, next we have question 4. It says the acid strength of the oxyacids of chlorine is as follows. Which statement best explains this trend? So the oxyacid with the most oxygens is the strongest. As you think about kind of like why that is and what's happening here, we define strength based on the ability for an acid to kind of like lose or donate a hydrogen ion. The more readily this is lost, the stronger the acid is. So as you think about like why that progression happens in a series of oxyacids, you need to recognize that oxygen is a very electronegative element. In other words, it's going to be able to essentially pull on the bond that exists here, even though it's not directly bonded to it, right? And so as oxygen pulls on that bond, it makes it easier for the hydrogen to kind of get, lost or donated. Now, in HClO, there's only one oxygen to do that. In some of the other oxyacids, right, we've got, for example, HClO2, we've got an extra oxygen, right? And as you grab additional oxygens, they are continually getting or putting more, or they're pulling more, I guess, on the that bond that's holding together the hydrogen, right? So it's pulling on this, even though it's not directly bonded to it, right? And so it's kind of pulling on these electrons that you see here, kind of weakening that bond, making it easier for the hydrogen to get pulled away, right? And as you add more and more oxygens, even though, right, it's not directly bonded there, again, it's sort of like pulling on that bond, pulling on these electrons, and just making it even easier for the hydrogen to get, come on now, pulled away, right? So in a series of oxyacids, as you think about kind of what's happening here, we are pulling those electrons away by the more electronegative oxygen, making that bond weaker. The more oxygens that you have, you just intensify that effect, right? So that's sort of the explanation behind what's going on in the relative strength of a series of oxyacids. Okay, next, here you're given a couple of acids and you're trying to identify which of them is the strong acid. This one is actually just getting you to think about how this works with very specific terminology. So I'm going to just jump down here and give you this answer, and then we'll talk about like why this is true, right? So hydrobromic acid, stronger acid, because the charge density around the ionizable hydrogen atom is greater. So as you think about what's going on with acids, again, remember that they are going to be stronger the more readily they lose their hydrogen. Well, in, for example, a bond here between hydrogen and chlorine, the electronegativity difference between the two is large enough to create a polar molecule, right? And it creates a charge density. And so what that means is when you add it to water, right, there's going to be some attraction between that water molecule and the positive region, in this case, on the hydrogen, right? And so it's able to then grab that hydrogen and kind of pull it away, right, from the rest of the molecule. So it ionizes it. In an example, like let's say it was hydrogen bonded to carbon, it's not really a polar bond here. It may be the teeniest amount, right? But there's not really a huge difference. We don't really say that this is a polar bond. And so there's nothing really for a water molecule to be attracted at. There's not really a charge density here for the water molecule to attract to. And so it's weaker, right? And so as you think about this sort of visually, right, I've got two atoms here. Their electronegativities are fairly close together, right? the charge density is not very great. Compare that to two atoms in which the electronegativities are very different. The charge density, right, positive region, negative region, is much greater here. And so as you think about this question, right, it's just sort of that, I guess, technical description in terms of like one of the reasons we define an acid as a strong acid. All right, next it's going to be some math time. Always really fun without a calculator. It says find the hydrogen or hydronium ion concentration of a 0.100 molar HCl solution at 25 degrees Celsius. The Ka is 1 times 10 to the minus 9. Now, I'm going to show you this first using an ice table, but eventually we want to get to the point where we don't need an ice table to solve questions like this, right? So as I think about my ice table, you want to be really comfortable writing out the equation for a Ka for any acid. Generally, this acid HX in water forming hydronium and its conjugate base. Now, as I work to solve this, right, we're asked to find the hydronium ion concentration. So we're basically looking for this down here. I'm going to drop the water because it's a pure liquid. And my initial concentration of the acid is 0.10. I know that this is going to be something less than 0.10 because this is a weak acid. How it's going to change, it's going to decrease by some amount. This is going to increase by the same amount x and also by the same amount x, right? Because everything's a 1-to-1 ratio. So at equilibrium, it's going to be 0.100 minus x. This will be x and this will be x. Now, Ka is defined as, like any K, a ratio of product concentrations to reactant concentrations. So it's going to look like this. You want to be very comfortable writing a Ka expression. And you're going to plug in the values that you know to solve. So 1 times 10 to the minus 9 is equal to x times x over 0.100 minus x. Right, I've just taken these from my equilibrium row and plugged them into my Ka expression. Now, you can solve this if you want to, but remember, it's really important that you can take advantage of the x is small approximation here so that the math will work out a little more easily for you. On our free response, you want to make a little note about why you're doing that, right? The difference between the initial concentration and Ka differs by a factor of 1,000 or more. On a multiple choice, you don't need to do that. But that's just going to simplify your math to 1 times 10 to the minus 9 equal to x squared over 0.1, which I'm going to convert to scientific notation since I don't have my calculator. And then to solve for x, right, I'm going to multiply these two values together. So 1 times 1 is going to be 1. And then when I'm multiplying numbers in scientific notation, I add the exponents. So 1 times 10 to the minus 10. And that's equal to x squared. And then to solve for x, I'm going to square root each side. So 1 times 10 to the minus 5, right? We're just going to divide our exponent by 2 when we're taking the square root. That's molar, right? That's equal to x. That is the hydronium ion concentration. Whew, now, that took me a really long time, and you don't have a lot of time, right? So a suggestion to get comfortable with, if you're not there already, is to be able to recognize that this is true, right? That Ka is going to be equal to x squared over the initial concentration. Sort of get to the point where you're sort of like automatically making that x is small approximation. And then, that's going to happen. This part of it should happen much more quickly for you. If you're not there yet, maybe skip a problem like this, save it to the end, and then when you have time, set up your ice table and work the rest of it through. But just something you want to practice and get comfortable with. In question 7, right, it's a really similar starting point. It's asking us for the percent ionization for a weak acid. It gives us the Ka. And you might be saying to yourself, like, how is this similar? In the last question, it was asking for hydronium ion concentration. And here, it's asking us for percent ionization. Well, remember this formula, hydronium ion concentration over the initial concentration of your acid times 100 is how we determine percent ionization. Not on your formula chart, something you have to remember. Hydronium ion concentration, right, is what we solved for in this earlier question. So the similarity is there, right? It's recognizing that you have to get hydronium ion concentration in both cases. So maybe let's practice that little shortcut where Ka is equal to x squared over my initial concentration of 0.4. Again, I'm going to put it into scientific notation. My Ka is given to me, right? So my Ka is 4.0 times 10 to the minus 7. So 4 times 10 to the minus 7. Again, I'm multiplying these two. 4 times 4 is 16. And then I add my exponent. So 16 times 10 to the minus 8 is equal to x squared. I'm going to square root each side here. And when I do that, I'm going to get 4 times 10 to the minus 2. That's equal to the molar concentration of hydronium. So that vastly speeded things along, right? So get comfortable with that. Again, if you're not comfortable yet, take the time, use your ice table, save this as a question till the end. But this is not the end, right? We need to then take this information and plug it back into this equation. So this is my hydronium ion concentration, 4 times 10 to the minus 2. My initial concentration of acid is 4 times 10 to the minus 1. Nope. I don't know how to do math. That is a minus 4. I was dividing by 2, and then I just thought about the number 2 and put it up there. But there we go. So as I work this through, right, it's also times 100, which I'm going to put in scientific notation. So I need to solve this, which is tricky, right? It's not easy to do without a calculator. So I'm just going to do the division first. 4 divided by 4 is 1. And then when I am subtracting, or when I'm dividing, I subtract my exponent. So 1 times 10 to the minus 3, right? Because negative 4 minus negative 1. And then I'm multiplying that by 100. Here I am multiplying, so 1, and then because I'm multiplying, I'm adding the coefficient, so negative 3 plus 2. 1 times 10 to the minus 1%, or in standard notation, 0.1% ionized. Whew. So again, a lot there. Easy to make mistakes, right? Hello, we made this mistake right here. I could tell I had made the mistake though because I was going to get a really large percentage. But that just comes with practice. I make mistakes. You'll make mistakes. And just do the best you can and try again. Last question for this set is this one here, right? You're given a set of 4 beakers, each filled with the equal number of moles of acid. And as you try to solve this, we're asked to identify which will have the lowest percent ionization, right? So remember that percent ionization is the hydronium ion concentration over the initial concentration of the acid times 100 to get that percentage, right? So as I think about beaker 1 and beaker 2, I need to know that HBr is a strong acid. Without knowing that, I can't answer this question. So it's so important to memorize those 6 strong acids. And if I realize that these are strong acids, whatever these concentrations are of the acid, the hydronium ion concentration is going to match that, right? They're not actually going to exist as HBr molecules. They're going to be completely ionized. Now, for the purpose of this video, I'm just going to put some actual numbers here. Let's say this is 1 liter beaker and this is a 0.5 liter beaker, but they each have the same number of moles of acid. We'll just say 4 moles in each of them, right? So here, 4 moles in 1 liter is a 4 molar concentration of acid, right? So for this beaker, the acid has a 4 molar concentration, and I know that all of them are going to completely ionize. So I'm going to get 4 hydrogens, right, or 4 moles of hydrogens in that 1 liter. So this is going to be, a 100% dissociation. Strong acid. In the smaller beaker of the strong acid, it's going to be really similar, right? I've got 1, 2, 3, 4 moles, but in a half a liter. So 4 moles in 0.5 liters. And again, I'm just making these numbers up because I don't have numbers, and sometimes the numbers help me kind of understand what's going on. This is going to be an 8 molar solution. But again, recognize that it's a strong acid. So I'm going to have 4 moles of hydrogen that completely come off of there. And 4 moles in half a liter is going to be 8 molar. So even though the concentration is different, it's still going to be 100% ionized when we talk about a strong acid. So these beakers out right away. If you look at the beakers on the right, here's really where we have to decide what's going on. Acetic acid is not one of the strong acids, so we can identify it as weak, right? And if it's weak, we're still going to use this equation, but recognize we're not going to have 100% ionization, right? The amount of hydronium we get isn't going to be equal to the initial concentration of the acid. So again, let's just assume 1 liter and 0.5 liter. Here I have 1, 2, 3, 4 moles in 1 liter. So my initial concentration of acid here is going to be 4 molar. In the smaller beaker, right, it's 4 moles in a half a liter, so it's going to be 8 molar, right? So the concentrations are different, but what's going to sort of, throw us off here or be different here from what we did earlier is the ionization. It's not going to be the exact same, right? But it's going to be fairly close. So for the purposes of this particular question, let's just assume that although the ionizations are not identical, they're going to be very close. And let's just say that they're each going to be 1 molar, right? And so as you think about the resulting percentages, right? This is going to be 1 out of 4.25 or 25% ionized, right? And 1 out of 8 is going to be something less than that, 12.5% ionized, right? So with weak acids, the more concentrated, the less ionized, right? And again, just think about your molarity equation, right? Moles equals moles over liters, and the actual equation for what it means for percent dissociation. Okay, that's it for day 1.